in your life with your
As usual, I'd like to thank our volunteers who help us organize these. These lectures were started by Michael Mackey here and Graham Bell, and we have the help of many volunteers, Ingrid from the museum, Eric Cook, Fred, some students, Lauren and Val and others, and it's always great to acknowledge their help to make this lecture series go. We also get support from mainly the Faculty of Science, but also some support from medicine, from CAMBAM, sometimes agriculture as well. We get some support, and as you all know, these lectures do not cost nothing to produce. We love to give them for free. We don't charge admission, but there are costs involved with paying for the reception, for advertising, security, cleanup, and so on. So we now have some new donation cards here in case you haven't seen these or would like to make a donation. You can mail them to the Faculty of Science. There's a dedicated account for the Cutting Edge Lectures, and any donations, of course, are get a tax or credit for them. So we invite you to make a donation. Some people make an annual donation. Some people give a few dollars each time they come. Whatever you can would be appreciated. Before I introduce our speaker, I'd like to remind you to turn off your cellular devices so that there's no interrupting during our presentation. Well, it's a great pleasure for me to introduce Professor Viacheslav Adamchuk. Janet, my wife, and I heard Viacheslav speak at McDonald campus a year ago to a retired reception, and it was really a very fascinating talk. And I thought this would be really a suitable presentation for this group here. So thank you for accepting the invitation. Dr. Adamchuk is from Ukraine. He's born in Kiev. He does come from a farming family. His grandparents were farmers, and that's what we have in common. My parents were also farmers. They came from Ukraine over 100 years ago. But I did not continue on in agriculture like my father, but Viacheslav did follow in the tradition of the family. He did his first degree in mechanical engineering at the National Agricultural University in Kiev, and then he came to the US to do his master's and PhD at Purdue University in Indiana. That was followed by a 10-year career at the University of Nebraska-Lincoln, and there he was in the Department of Biological Systems Engineering. He came to McGill in 2010 into the Department of Bioresource Engineering and has been very active here in teaching, public outreach, and in many research collaborative projects. He has received a number of awards for his work, including the Pierre Robert Precision Agricultural Young Scientist Award presented at the 9th International Conference on Precision Agriculture. At McGill, Viacheslav is also a member of the Center for Intelligent Machines, and on the international scene, he is the secretary for the International Society for Precision Agriculture. In one sentence, his research interests are focused on the development and deployment of on-the-go soil sensing technology to enhance the economic and environmental benefits of precision agriculture. Now, just what that means, we'll hear from Dr. Adamchuk. Please.
Thank you for the introduction, and good evening, everybody. It's an honor to be here and to share some of ideas, visions, histories, and jokes, maybe, with regard to smart technologies and what they can do for us in agricultural and natural resource management arena. And I will skip introduction, but just had this slide here because a lot of examples that I'm going to discuss are related to those places. Our department, we are the only engineering department on McDonald campus, and it's a fascinating facility. If some of you haven't been, we have some fields, some forest, and that's where we test a lot of piece of equipment that I'm going to discuss. So our research team is called Precision Agriculture and Sensor Systems. We cover these two key domains. And primarily we work on development of proximal soil and plant sensing systems. Then we also dedicate substantial effort toward geospatial data processing and management, and also practical implementation of precision agriculture, and the latter seems to be a topic of interest to many, as this is pretty much our future, which is actually a question of what is our future. So this is an example of a tractor without cab, or milking system without hands, and so is that it? So that's well. Let's discuss this in depth. Like, I took this particular graph from one of reports. It's been put together by business advising group in Germany, and like 2 or 3 years ago, and they put like this framework of how these agricultural technologies are evolved. Again, this is non-agricultural people making the report for agriculture, pertaining to agriculture. So what they identified is automation, robotics with different layers. That's getting developed. Imagery and sensors, big data and digitization, so deep learning technique, artificial intelligence, is all part of the system. And also they added this bioengineering with different meaning to these terms, and they are talking that maybe 20, 30 years from now, this all will converge together, and there are some discussions of how it's going to happen. In terms of the value, in the same report they also mentioned that by 2020 they estimated that it would be $4.5 billion worldwide precision agriculture as a business. So apparently there is a lot of groups, especially like in emerging economies and so on, that interested in this. So there is incentive to invest in technology, and the question is why? What's helpful? How many of you think you know term precision agriculture? Okay, well, this is easy, because in every group that I normally talk, people have definitions, they think they know the definition, but there are so many definitions that it's difficult to judge which one is correct. I kind of like this one taken from Wikipedia at one particular point, because even there it's changing completely and different in different language. But precision farming, precision agriculture is a farming management concept based on observing and responding to intra-field variations. And a lot of people still believe that this is all precision agriculture does. You go to the field, you recognize, okay, there is some variability, so let's do something different in different parts of the field. Which is true to some extent, but today it's much more than this. It's about whole farm management with the goal of optimizing returns on inputs while preserving resources. So it's basically use information technologies to improve profitability, or anything to do with economics of farming as industry. It's improving environment, or reducing negative environmental impacts that agriculture does, and improving social status of food production industry. We can see that with precision agriculture, a lot of young people and IT-oriented specialists suddenly finding precision agriculture as an interesting area to work in. At the same time, there is a lot of misperception. That's why I ask a question first. And it's not a magic toolkit. So there are certain things that precision agriculture doesn't do. It doesn't resolve general production problems. As a matter of fact, a lot of times when we start implementing precision agriculture for a particular environment, we talk about general production system, we're finding errors. It's basically like reviewing your checkbook and find, okay, this is where I'm spending the most. So that helps, but it doesn't by itself. It doesn't resolve those generic production problems. This also doesn't happen. Like if you have certain conditions, certain type of soil, we have to deal with this. Yeah, we cannot do rain dances or anything like this. It's well, maybe some, like it's in your department there are some modeling, like like we don't like this model. Can we generate better model to have better rain? But again, this doesn't work like this. And we have a lot of farmers getting excited about this technology and forgetting about that they need to maintain equipment, calibrate equipment, and do everything else. So this all has to take place at the same time. Also, produce have to be sold. So we have this economic constraint, but we have tools that can help visualize all of these problems. And then once you understand the problem, like diagnostics is basically part of treatment. And why we are talking about precision agriculture as a mainstream technology? In my opinion, this global navigation satellite system based outer guidance, that's technology that's been adopted the most widely worldwide. And this is an example why. Our group developed an ISO standard that measures accuracy of outer guidance system. So basically you have GPS on the equipment, you drive across the field and you don't touch steering wheel. So we have issues related to vehicle dynamics, to accuracy of GPS and so on. And this results from actual test. We took a couple tractors, that's why we see those two sets of lines. And blue means that it's pass to pass, so we basically we're going through the same area multiple times. And red, we went through the same area multiple days when we have different constellation of satellites in the sky and so on. And we were making these measurements using an optical system that can identify errors as big as 1 millimeter. And what we see here is that when traveling about 2 to 3 meters per second, normal field operation speed, we can get 95% less than 2 centimeters. That's this much. From day to day. So, and that's like, I mean, it's not science fiction, so it's today. We can do this well. Of course, with different factors, if we have less fine, unoptimal adjustments of the controller, or different difficult field condition, different type of equipment, low-cost solution, there is going to be bigger. So there are different type of application and different costs associated with technology and so on. But this is like having this capability allows dreaming about different type of solutions. This graph I took from another report. It's a dealership survey. This is 2015. Purdue University does this every 2 years. And we can see that some technology we have relatively slow adoption. Some it's already been adopted by majority of farmers, and this guidance is the ones that actually propelled system adoption through 2000s until now, and it's still becoming one of most popular solutions. From system viewpoint, it's not always when you actually go through the field. It's also logistics in terms of fleet management and so. It's like in every day. Now, driving direction, you use cell phone. Trucking companies, they know location, travel speed of every vehicle that they operate. In agriculture, same way. We were doing these activities trying to see how multiple units can collaborate together, how dispatch, technical services can use this information. Basically on the screen you can see like 400 or so vehicles, where those are at any specific point of time, who is driving them, what's happening, is there a technical problem that needs to be resolved. In terms of technology, this first definition of precision agriculture, this is an example of equipment that has a lot of machines, but what it can do is plant, put liquid fertilizer, put 3 different types of dry fertilizer, so 5 different products, and each of those products will have different rate according to the local needs. And more important, this information is developed by an agronomist who is sitting 200, 300 kilometers away from the field and putting this information through cellular communication. And I'm talking about 2012. Now all mainstream equipment suppliers, they have this capability and this is feasible to do. However, the question always, how much to apply? And from viewpoint of control, I like to look at this from 2-layer perspective. So we have to make decisions like what to plant, related to weather, economics, related to risks that we have in general with agriculture, and of course variable rate technology. In general terms, the first one, that would be 70 to 80% of benefits that you will see. Like those systematic decisions, they are very important for agriculture, especially right now when we have weather forecasting better, when we have ability to look at multiple scenarios at the same time. And variable rate technology, that's fine-tuning, that's pretty much looking at smaller parts of land. And we do have some people dreaming about planting by individual crop, basically by individual kernel. We have technologies that we can have location and some information about each individual seed that we plant in the farm. So first example that I'm going to show here is in the area of artificial intelligence and decision support system. That's what we are working on right now. What it does is basically a server, so a user can provide information about, yes, this is the farm, this is what is happening on the farm, gives this information to the server. We have a database that contains information from multiple trials taken from different areas within Quebec, within Ontario, that has information related to weather conditions, related to general conditions of production at that time. We also have online resources such as Chicago Board of Trade, like when we go and see what the prices for commodity, what the prices for fertilizer. We also have weather parameters. We have some information about soil that can be considered at the same time. And putting all this together, we can generate some recommendations of this is supposed to be done, this and this is going to be our output. But more interesting that the same user, if they have information about what they did with the field and what they get, they can input this information to the database. So it works like continuously updated database. More information is put in, the more accurate is the recommendation. So this is a site that runs this decision support system, and we're still in testing mode and doing some fine-tuning and validation. But once you put the data in, you get this type of report. And new things that we are trying to impose is that we don't give one value. Like, yes, we get the number that, okay, this is most economical, so here it is. But we also tell what would be that number if you did something different. And what are the chances of being profitable, or more profitable, less profitable, if you don't obey this recommendation. And agriculture is industry with a lot of uncertainties. So basically, in many cases, it's a combination of factors, including risk preference, that identify what farmers or their advisors need to should be doing. On the low scale, on the other side of this, we proposed technology that's called smart tractor. Few people know, but middle and large size vehicles already have 3 computers on them. So what we suggested to do is to get tractor controller additional job on actually doing variable rate technology, similar way to auto guidance. The way auto guidance works, you come to the field, you start driving, you press point A. So then you drive certain distance, you press point B, and that's it. The vehicle, remember that this is a line, so every other line will be parallel, will be in strong geometrical configuration with that initial setting. And this is interface that we built. Also, you can see A and B. So, but now instead of changing travel direction, we changing travel speed, we changing different parameters like valves and so what the tractor have, and it's a combination of using sensors that's already in the tractor, using external sensors, operator inputs, maps, and things like this. One key component that's actually have to some extent revolutionized agriculture equipment, it's this little plug right here. Very few people would notice it, but it's actually isobus port. That's the one that allows communicating vehicle to external devices like machinery, sensors, and so on. And all of those protocols of communication, they will standardized. One other example how this can work. This is a harvester that we have at McDonald Farm, and we just have ultrasonic sensor in front, and it looks at biomass and changes tractor speed to adjust to the amount of biomass to cut, so that we never plug the machine and we always go with optimum speed. And it's done automatically. It's like cruise control, but you have variable speed according to the conditions. This is another project that we piloted a few years back. It's a planter that actually changes the depth of planting depending on the moisture condition of the soil. It's a little sensor that we put in front that measures how wet soil. It's basically capacitor sensors that we constructed, and it operates actuators that change in depth as you drive across the field. The idea is that if it's too wet, you put seed relatively shallow so that emergence be uniform and you have best yield possible. Machine vision. There are many different applications of machine vision in agriculture, and the number of options is still growing. This one we built for a couple local organic producers that they're not allowed to use chemicals, so they just remove weeds mechanically. And it's a low-cost surveillance camera, just all the trick in software, as some say. Just looking at the row, and then there are some steering mechanisms that we control and can adjust the position of the cultivator in real time. So basically you can produce operation at higher speed. Quality of operation doesn't change through the day, and you can have operators with low skills like myself doing this without damaging a lot of rows. So just this is a few examples, but one critical issue that I wanted to bring here is this is what's known as site-specific crop management circle. So there are different operations, and there is this what we call mapping and data mining season. It's what farmers do these days during winter. So instead of going to Florida, now we sit in front of computer and looking at data. So sensing is a critical component of this, and we can use either imagery in season, off season, or sensors, real-time application. That's actually when we sense and make management decision in real time, or we collect data, create maps, and then make management decisions. So now I'd like to talk about sensing part, because it pertains to many different areas, including agriculture. And of course, there is a nice exhibition here in Ottawa. It's called The Art of Engineering. So it's kind of inspired. So if we are talking about engineering, so let's talk about art first. And this nice painting from called Five Senses. So here we have look, we have listen, touch, smell, taste. So all of the senses are here. And with sensors for agriculture, like for soil sensors, that's exactly what we do. Not many things new, however, we do go a little bit farther than just the basic senses. We look at the entire spectrum of electromagnetic waves, and a lot of interesting information at short waves, microwaves, visible and infrared, gamma ray spectrometer has promise when it comes to agricultural problems. Some people are playing with terahertz. So all of those sensors been tested, implemented to different extent. I just will show a few brief examples. Also, it's important that some of the sensors are used for remote sensing platform, and there are different groups that look at this: satellite, aerial, UAV, very popular in agriculture. We have like every year we have about 10 or dozen different groups looking at UAV solutions for agriculture. It's all IT groups and high-tech industries. And proximal sensing. That's when you make measurements when a sensor is located less than 2 meters to the target, and those sensors can make measurements on the go, on the spot, or stationary, or make profiling, because a lot of times we need to have measurement representing different depths. So, as example, this is field units that we normally use to characterize land with high density information. So, what you see on this photograph, this is actually base station. So we have RTK receiver. It's very quality topography data. Quality topography information gives like 70% of information related to landscape. Because why we have differences of soil? Because of differences the way water moves, the way things happening with management, etc. The one on the top, that's actually SLAD. That's an electromagnetic induction instrument that has different coils at different distance. So one coil creates magnetic field creates eddy current in the soil, eddy current creates secondary magnetic field in secondary coils, and just by looking at those relationships, we know ability of soil to conduct electrical charge. Ability of soil to conduct electrical charge relate to many properties, including salinity. Like everybody done this experiment in school, right? You take a glass of water, electricity doesn't go, you put some salt, electricity goes. Well, here it is. But in this area, like Quebec, Ontario, we don't have a salinity as problem as such, so we can look at different soil types, because like if it's soil that's heavy, that's or clay, or soil that's wet, that's conduct electricity better than dry sand. It's a good isolator. And we use this data to define areas where to sample, how to characterize landscape in general. The one on the bottom left, there is a company in Ontario that does this service to farmers in the area. That's a gamma ray spectrometer. It's a passive spectrometer, it doesn't emit radiation, but soil itself is radioactive material by nature. It's very low level, but it has isotopes of potassium, sodium, uranium that actually continuously emit signal, and this instrument, works like gear counter, can register while driving across the landscape, and that this information also can relate to soil mineralogy and a lot of differences with it. This is one of technologies that I also wanted to show that we developed a few years back. It's like a mini chemical lab. I think this is a good time to show how it actually operates while driving. So this is one of vegetable producers in Netherlands is using this system. So it measures lateral conductivity using coulters. It measures optical reflectance of soil using Schenck. And then this instrument on the back, it collects soil, then bring in contacts with a few ion selective electrodes and make measurement of soil pH, acidity, which is quite important soil factors that affects fertility. And you're just basically going back and forth and you making like this. This unit we also operate on McDonald campus, and right now it's actually in Ontario. We're looking at some fields there around Guelph area. It can penetrate 1.2 meters deep, and it has spectrometer, electric conductivity electrode, and load cell. So we get three parameters at the same time. We're looking at visible all the way to the infrared spectroscopy, about 400 to 1100 nanometers. And what it allows us is to get complex assessment of soil at different depths. And with appropriate model, we basically regenerating three-dimensional model of entire soil mass. And there are some commercial groups that working on a similar approach, and it's another technology that can be helpful. In general, spectrum is an important measurement when it comes to agriculture. Like plant, no question about it. Like we have this blue, green, red, near infrared. So every time we have vegetation, we can see it through optical parameters, and there are several biomass indices, chlorophyll indices, and so on that relate to this. And I will be talking about plant sensing later on. On soil, it's a little bit more boring, but with improved technology, with better quality sensor, with sensors that go into mid-infrared or Fourier transfer infrared technology, we have ability to identify specific features on the spectrum that relate to given soil properties like texture, organic matter. It's in even some chemical properties we can identify at regional scale, field scale. There is also global spectral library. We just published a paper a couple of years ago that's looking at ability to predict a dozen different parameters across the entire globe. How big should be a sensor? Like this is a sensor. It's actually a bunch of sensors, right? But camera is one of the sensors. This little app looks at color, and by color we can define carbon. So, and that's organic matter. That's also very important when it comes to agriculture.
Which one had the most carbon? Which color had the most carbon?
Oh, darker.
The darker.
Yes, normally dark black. Soil microscopy. That's areas that we started again a couple of years ago. We're still working on it, but we found that like it doesn't cost a lot these days to look at soil at this scale. So we can see aggregation, we can see individual soil particles. If you're lucky, you see a little bit of life. It's a very, very tiny worm. I don't know how we found it. And this is a relationship between percent sand in soil, measured by the lab. They normally use hydrometer method, and predict it based on microscope. So it's a quite valuable technique. If somebody used hydrometer before, then know what I'm talking about. It's a very labor-intensive process. For developing world, this is another prototype that we built, just basically to take soil sample, but you can make measurement of pH, or we also done some work with nitrate right there in the field. And it will also record GPS coordinates or so, and you can go from one point to another without machine. Soil biology, it's actually very important factor, and right now we have more and more groups of people looking at, okay, we have physical characteristics of soil, we have chemical characteristics of soil, but what about microorganisms, because they affect of how the soil behaves. So this is one of prototypes that we use to assess concentration of CO2 within soil profile. So it basically has a pump, so we quickly suck air from the soil and measure the change of concentration. And right now we're working on a set of these chambers. They are more passive, they don't have pump, but we allow them to stay a little bit longer, and we use wireless sensor technology to monitor how level of CO2 changes inside those chambers. On the spot analyzer, that's our prototype system. That the goal is to combine multiple sensors in one unit, and the way it works, it just basically makes a hole in the ground about 10 centimeters in diameter, 10 centimeters deep, and then we have a suite of sensors that we put on the bottom of that trench, and at that particular place making multiple measurements. Some of you might recognize this vehicle. So, yes, so this is Curiosity, and what we are trying to do is pretty much the same at a tiny fraction of budget that NASA has. Well, we do have grand challenge, and this is our grand challenge. On the left, you see different properties. So this is what we need to know to make decisions. On the right, it's pictograms of different sensors. That's what we can measure. And this is what makes my everyday interesting. Because we have this multiple effects. So that's where different modeling technique, including artificial intelligence, that getting helpful. But the key word is sensor fusion. So that's been main trend in proximal soil sensing science. And as one example is the system that I already showed, that using galvanic contact resistivity method to measure electric conductivity, two wavelengths, optical reflections to measure soil color, and antimony ion selective electrodes to measure soil pH, and plus topography. So every time you go through the field, you get RTK level elevation. Lab data is still important to do site-specific calibration, which is required for this type of operation. So how this works, it's a system. It's a system. We have sensing data, topography data, yield data, which is also high density layer of information coming from harvester, imagery, whether from drone or from satellite or from high altitude airplane, and we combine it with lab data and farmer experience. Farmer experience is absolutely essential piece of information to make proper decisions. And then when we look at this together, we can make decisions whether go into variable rate technology, best management practice, or some combination of both. So how to combine these multiple layers together? This little piece of software that we built again a couple years ago, but we still making some modifications, takes multiple layers and grows what we call like clusters, established clusters, but unlike other clustering methods, we try to make sure that those clusters are contiguous, so that we can establish zones, and also those little yellow squares, that's the most representative points within those clusters. So those points in the field that where we go and do additional exploration as needed to develop decent model. This example here, one of the experimental fields in Ontario, EC, pH, elevation, getting together, so those areas, and the darker the areas, the more special, the more unique those areas. So blue, that means that doesn't mean that all blue is the same. Blue means that it's different than the rest of the field. What else we can do with that information? Some soil parameters like texture, organic matter doesn't change overnight, but some do, like moisture. So how to combine together spatial and temporal? This is one of examples, EC map with topography again, and we put in wireless sensor network. It's like 10 years ago, was brand new, now many industrial entities already doing this. But the trick here is to get, every 15 minutes I can get water stress estimation for the entire field. I can make decisions to irrigate, not to irrigate, or to how much to irrigate, or be it frost, like in orchards or so there's different decisions that can be made based on this information. I mentioned drones. This is what we fly. It's not the best, but this technology is getting popular very rapidly. But like even 7 years ago, we were able to already take off automatically, land automatically, and collect all the images and use this information again through the same decision support system. Crop. Crop is one of the best sensors for soil. Like if crop doesn't feel good and so on, there is something wrong with conditions. So how do we estimate this? This is a system that when we integrated multiple sensors, so we're looking at temperature of canopy, using ultrasonic sensor to look at biomass, using optical reflectance to look at chlorophyll, and combine this information together and gives us status. And this is one of the sprayers that actually does real-time application. The way this technology works, and there are quite a few producers that are already using it, when the sprayer goes, it has some sensors in front. It's looking if crop is hungry or it's in good health conditions and so on, and then apply nitrogen fertilizer as needed. So the way instead of growing algae in St. Lawrence River, some of my jokes don't translate very well. You just simply, in the beginning of the season, put as little fertilizer as possible, just to get to the point where you can make adjustments, and then make adjustments according to what you see from crop. And we also go in for even further to that, is combining crop information and soil information together to make best decision. Like right now, we're working with Roberto is here. He's working on using laser to characterize soil, and using ultrasonic sensors together also as one package. And we're looking at vegetable crops. Precision horticulture, that's industry requires a lot of automation, a lot of sensor technology, and this very little sensor like this. Yusu is also here, developer of the sensor. So what it does, every time, and this is production, just like as you go through New York and before you leave the country, there are some fields, so that's one of those fields. They collect lettuce, like it's already pre-packaged to go to the store, and so it goes in the bin. We measure the weight of the bin with this weight, but information from the scale is sent through cellular communication to the server, and manager at any point of time can see where and how much of produce they generated. And this is big help in terms of management decisions and etc. Right now we're also working on online yield monitor system for such crop as onion, carrots, and in this situation it's not just yield, it's also how much. Apparently, we as customers are very picky when we come to the store, like a small, big, like we don't like this, and so on. So farmers, they need to make the decisions, but they don't know what they are harvesting. Like it rains tomorrow, it rains full week, it's flooding this year, and so a lot of factors that might affect this size, and so having this real-time feedback helps. Precision apiculture, it's another system that we built again a couple of years ago. We looking at conditions within each hive, and using sound, temperature, humidity, we can identify if everything is going well, and if any health problems within the hive, we can see it before things get bad. Water quality. Some people say that lakes are uniform. Like we also believe that lakes are uniform, but we look this couple ponds that we have on the farm, on McDonald farm, and you can see that well, it's not really the same. It's small ponds, but still like bank and different parts of bank. So we built this robotic boat and a suite of sensors. So we're looking at dissolved oxygen, pH, nitrate, things like this, and just driving across the boundary of the lake, we can identify what the source of pollution and where fertilizer is drained to the lake, and like who is responsible and things like that. So as a bottom line for this presentation, I'd like to this is key statement in my opinion, that when it comes to precision agriculture, there is no situation where it doesn't work. But it's not always this technology should work everywhere. There is no such thing as one size fits all. It's all independent. Like one of my former instructors was a professor of agricultural economics, and he's an expert in precision agriculture. So some people say that, what about economics of site-specific crop management? He said it's site-specific. That's so. That farmers that I saw in the beginning, like enjoy and drink while machines doing work, is actually probably in the future will look at those problems, and I do calculation of economics and so on. So also, as was mentioned, presently I'm secretary for the International Society of Precision Agriculture, and this is next year is a big year for us. Because 14th International Conference on Precision Agriculture, which never left United States before. This conference was always somewhere in the United States. First time it's in abroad, and it's in Canada, and it's in Quebec, and it's in Montreal, just a few blocks away. So if some of you could make to this meeting, there is much more information. It's going to be opportunity to meet world most lead scientists in this area, and thank you very much for your attention, and I will be open to any questions or suggestions.
Thank you so much for coming all the way from campus to speak with us. I have a small token of our appreciation on behalf of the museum.
Thank you.
So we have a little bit of time for a few questions, if anyone has any. Yeah.
To what extent is this precision agriculture confined to large agribusiness operations versus small farmers?
Good question. There is not correlation between precision agriculture and size of operation. There is correlation with different type of applications, because to start precision agriculture, initial cost is zero. Like you can go to Google Earth, get the maps, using cell phone for GPS positioning, and we see decision changing. Like at the beginning, people were using shovel and bucketers to like. My grandfather used to use shovel to apply manure in the field, and he would apply less at the edge of the gardens. Like why? Because there is a couple pear trees and they create shadow, so nothing grows anyway. It's like now I know that it accumulates phosphorus, and if we put in more, we'll burn potatoes. So, but he did precision agriculture like 50 years ago, and actually, if we're looking at literature, even Platon was writing about soil variability and so on. It's an ancient problem. Just the fact that GPS is in every, like, it's popular device, and electronics is getting less and less expensive, it's becoming more affordable. You don't need to go for the highest, the best, like the biggest piece of equipment to implement variable rate technology, and to monitor, just basically to summarize all the information about your farming scenario. We worked a lot with like paddy rice producers in Malaysia or so, and it's relatively small farms, and they do precision agriculture.
It sounds as if you want to be a farmer, you'd better go into information science. I don't know if you want to say something about how you think a farmer should prepare or be educated, if that is the correct word.
Well, it used to be 20 years ago. Like, in University of Nebraska, I worked in extension, and part of the job was to go and talk to farmers, and we would try to convince, and there is like different generation of farmers, different skill sets. So, but these days there are a lot of companies that like service providers. So you basically sign up for a particular service, and you get in your recommendation. It's same way as in general computer usage. Like 20, 30 years ago, when we did computer, like normally you use it to write some code or so. Now everybody is using it every day. Precision agriculture is the same way. You can have all your data available to you. You know the information about your equipment, and more and more companies offer cloud storage for all precision agriculture data. Google Earth is free. You can look at your farm without paying anybody.
What do you think about restricting rules for using pesticides in Canada?
Another good question, and that's not necessarily relevant to precision agriculture. That's what I was talking about. There is this systematic changes to production, and then there is this optimization. So in terms of which type of plant protection system to use, that's responsibility of farmer or farm operations. There is like policy and so on. But with precision agriculture, we can minimize use of chemical. Like I have a colleague working in Dalhousie University with optical system on wild blueberry. They reduce pesticides 70% because they apply only when they have problems. But operations like this is it's one of vegetable producers here again on South Shore. It's automated machine, so doing weeding. No pesticides. And actually, yeah, driver is right there.
No more Mexicans.
There is nobody in the. It's today. Means there is some insecticide or something else that because there are different problems that you still need to use chemicals. But the point here is that you need to make decision in terms of what to do, but how much and how to minimize this effect. That's what technology is for.
Excuse me, do you think it's responsibility of farmers or the state?
Well, a little bit of both. There is policy and there is decision makers. It's a synergy.
We'll go at the back.
Yeah, I'm going, this is regardless, but I was surprised and maybe happy because I never expected I would see the person from Nebraska because I just moved from Nebraska to Detroit last December. But
the answer is yes. I didn't do projects in Korea, but I did look at small field production in China, Japan, Philippines, and Malaysia, and everywhere precision agriculture is suitable. We looked at because like in the paddy production you're supposed to compact the soil, so just whether it's compacted, how to control depth of layer, because everybody is putting more water than needed, so control of water level on the production field, application of fertilizer. I've seen in Malaysia a lot of people, they would get fertilizer for free, they don't apply because technology is not available, or so. It's also possible to do. Right now there is a trend of using drones to spray those small fields, and sometimes people talk about like crossing the boundary, so service providers, they can do multiple fields at the same time. Like we had only in Malaysia we had only one sensor, 7,000 hectares of land, so pretty much the entire community, and it's all like one family, one field, maybe 1 hectare at most. So, and all information is publicly available, and farmers can benefit from that. So there are different ways technology can be implemented.
We'll take one last question right up here.
Our country is going through a frenzy for marijuana. Is anybody doing precision agriculture?
I hear so, not only that, but there is like medicine crops and so on, so which is like when precision agriculture has biggest economic impact, when you have expensive crop, when you have expensive inputs, and when things are wrong. So if you're in the middle of Illinois and corn is nothing, and then fertilizer is free, then of course it's like you get benefits through ergonomics or through some other channels. But if you have expensive crop, expensive fertilizer, and a lot of production problems, that's when technology can help.
Excellent. Well, thank you so much again for
Thank
coming
you.
And I also want to thank you, our audience, for attending tonight. If you enjoyed the lecture and would like them to continue, please consider donating. We have some cards up here. And I'd also like to invite you to join us at our reception, which will just be in the entrance hall on your way out. Thank you very much.